Okay, section 5.7 is what's called differential equations. If you listen to the title of that, it kind of sounds like it's got a derivative. That's kind of key. Differential, kind of derivative, equation. You're going to have a derivative in the equation. Really, that's kind of what a differential equation is. So our objectives: determine general and particular solutions of a differential equation, verify that a function is a solution of a differential equation, and then solve differential equations using the exponential growth or decay model. Our vocabulary: differential equation. Like I said, a derivative is in the equation. General solution or particular solution, initial value problem, and then exponential growth. Technically, you could put decay on there as well. Okay, so the definition: a differential equation is an equation that includes a derivative. That's what I was saying. The solution to a differential equation is a function that satisfies the equation. So when we say solution, what we're typically saying is because there's a derivative in the equation, when we solve the equation, we're somehow getting rid of the derivative, so we're kind of in the mode of taking an antiderivative to solve the equation, to get back to the original equation that the differential equation came from. For example, if I tell you that y equals e to the 6x is a solution to the differential equation, when the differential equation here is y double prime minus y prime minus 30y equals 0. Well, we can show that this is true by finding derivatives. If we take the derivative of y, we take the derivative of this, you get y prime equals 6e to the 6x. If you take the second derivative, which is the derivative of y prime, you get 36e to the 6x. All you then have to do is take these values and plug them in to this equation and show that it's actually a true solution. So y double prime goes right here. Okay, that's the 36e to the 6x. Y prime gets plugged in right here. That's the 6e to the 6x. And then minus 30y, well, y was the original function right there. That gets plugged in for y. So then as you can see, you get 36e to the 6x minus 6e to the 6x minus 30e to the 6x, which is 0. Because 36 minus 6 is 30, and 30 minus 30 is 0. So there you go. That would show that that is a solution. Actually, showing something as a solution to a differential equation is probably one of the easier things to do. You have to be able to take derivatives and then do some basic addition and subtraction usually. Okay, so we're going to show that e to the x squared is a solution to the differential equation, which is given to us right here. So it says y prime equals 2xy. So basically we need to figure out what we need. Fortunately, x is just x. Y is the original equation, so I'm going to need y prime. I'm going to need to take the derivative of e to the x squared. Well, it's a bit of a chain rule. It's going to be e to the x squared times the derivative of the exponent. The derivative of x squared is 2x. So that y prime is going to get plugged in for that. So we're going to get e to the x squared times 2x. I'll put the 2x out in the front. Equals. And then I've got 2x, and then I'm going to replace this y with this y, which is e to the x squared. And there you go. As you can clearly see, 2x e to the x squared equals 2x e to the x squared. That is verified. Okay, let's go ahead and show now that c e to the x squared, y equals c e to the x squared, where c is some constant, is also a solution to exactly the same differential equation. So what I need to do is I need to find y prime. So we're going to do y prime. C is a constant, so it stays there. E to the x squared, and then times the derivative of the exponent, which once again is 2x. So we're going to go ahead and plug that in. That's y prime, so it's going to go on the left of my equation. So I get 2x c e to the x squared equals, and then on the right side I get 2x, and then y was c e to the x squared. Once again, those two things are exactly the same. Done. We've proved it. In number 2, show that y equals 4e to the x plus 5e to the 3x is a solution to this differential equation. So it looks like I not only need y, I not only need y prime, but I'm going to need y double prime. So let's find those two things first. So y prime, my derivative, is, let's see, it's going to be 4e to the x. That doesn't change. The next one will involve a little bit. It'll be plus 5e to the 3x times the derivative of 3x, which is 3. So let's simplify that. That's 4e to the x, and then 5 times 3 in the next one is 15e to the 3x. That is y prime. Now we need y double prime. So the derivative of y prime is 4e to the x. Okay, we're going to have another bit of a chain rule here, so that'll be 15e to the 3x times 3. So simplifying that, it's going to be 4e to the x. 15 times 3 is 45. E to the 3x. There's y double prime. So now we should just be able to plug these things in, and hopefully this will work out. So y double prime is this one right here. So that's going to be 4e to the x plus 45 e to the 3x minus 4 times y prime, which is this one, 4e to the x plus 15 e to the 3x plus 3 times y, this was y right there, 4 e to the x plus 5 e to the 3x equals 0. So now let's go ahead and distribute and simplify, and hopefully all this stuff on the left side adds up to 0. So we get 4 e to the x plus 45 e to the 3x, distributing that negative 4 through, so we get minus 16 e to the x minus 60 e to the 3x. Now we'll distribute the 3 plus 12 e to the x plus 15 e to the 3x equals 0. So basically now we just need to combine like terms, and hopefully this works out. I've got 4e to the x minus 16e to the x. So 4e to the x minus 16e to the x is minus 12e to the x plus 12e to the x. That's 0. Good. Those are all gone. And then we've got 45e to the 3x minus 60e to the 3x. So it's minus 15 of them. And then plus 15e to the 3x. Good. All those are gone. So what we end up with is 0 equals 0. And that is a true statement. That is a solution. All right, so the function that we use in example 2 is not only a solution of y double prime minus 4y prime plus 3y equals 0. In fact, any function of this particular form right here, where a and b are constants, will be a solution. So I can make a and b any constants I want to, as long as it follows that form. And believe it or not, when you plug it back into here after you take derivatives and everything, it will work every single time. So it's also true that every solution of that differential equation will have to be in that form. The set of all those functions that solve the differential equation represented a family of functions. This is called the general solution of the differential equation. So the ones with the a and the b in it, that's the general solution. The one that we came up with, or the one that was given to us with the 4 and the 5, this thing right here, is called a particular solution. It is one particular solution that works. The a and the b part is the general solution because we could plug anything in there. If the differential equation happens to be in the form of dy dx equals some function x, then we can find the solution by integrating. You can actually take the integral of lowercase f of x dx, you get the capital F of x, which is the antiderivative, plus c. So again, if we start off with this, dy dx equals f of x, if you take the integral of both sides, because what you do to one side, you have to do the same thing to the other side, with respect to x, What you can see over here is on the left side, the dx's cancel out, and you're just left with the integral of 1 dy. On the right side, you're just going to have the integral of f of x dx. The integral of 1 with respect to y is just going to be y. The integral on the right side is the capital F of x plus c, and there you go with exactly what we said we were going to get. So, in example 3 here, whoops, went too far, y prime can be written as dy dx, so it follows the right form. So we can write this as dy over dx equals 2x. And then we can go ahead and integrate both sides with respect to x. So on the left side, the dx's cancel out, and what I end up with is the integral of 1 dy equals the integral of 2x dx. So the integral on the left side is just y. Integral on the right side is x squared plus some constant c. And that's it. That's the general solution. It's general because it has the plus c. If we were given some kind of an actual initial condition, like we were given some particular point on the original function, then we could have actually found c and we would have the particular solution, which is what we're going to do in example 4. It's a different function, but it's the same idea. So a differential equation is often paired with its particular function value. In this case, that gives us a particular function value because y of 0 equals 3 means when x is 0, y is 3. It's a point on the graph. It's the point 0, 3. It's actually a point on the original function. So in order to do this, we're going to use that at the end to find c. So the first thing we do is we solve the initial condition problem by doing the integral. So we've got dy dx equals 2x plus 1. I've left some space there because now we're going to integrate both sides with respect to x. So on the left side, the dx's go away. Once again, we are left with the integral of 1 dy. On the right side, we have the integral of 2x plus 1 dx. So let's go ahead and integrate. The left side gives us y. The right side is going to give us x squared plus x plus c. Now's where the initial condition comes in. The fact that we know that x is 0 and y is 3 is going to allow us to plug those values in and find c. So if y is 3, I'll plug 3 in for y. I'll plug 0 in for the x's. And of course, 0 squared plus 0 is just 0, so we get that c is 3, which makes our actual particular solution to this y equals x squared plus x, and then we'll change c to 3. And that is how you do an initial condition problem. All right, probably the shortest video that we've done in quite some time, but there you have it. And actually, I didn't mean to get your hopes up there. I was kind of lying to you. I forgot we have one extra page to go. Sorry about that. Still won't be extremely long, but won't be that short either. All right, so differential equations are important because they allow us to describe the rate of change or the derivative of a quantity in an equation, then solve to find a formula for that quantity. So that sounds a little hypothetical. I understand that. A concrete example is, suppose we're studying population. We want to, we expect the population to increase at a rate roughly proportional to the size of the population, meaning that a small population is going to grow more slowly than a large population will. So if you think back to algebra, the phrase proportional to, or y is proportional to x, basically means you're going to have y equals kx, where k is some kind of a constant of proportionality that you multiply in. Well, in this case, it's the same idea, except that this time our differential equation, or our rate of change, is proportional to the actual population itself. So how the population is changing is proportional to the population itself. And that's where you get that differential equation right there. Well, without going through the entire process of how to find it, when you take that differential equation and you find a general solution to that differential equation, what you end up with is a population equation that is this. The population is P sub 0, which means your initial population, times e to the kt, where again, the k is that constant of proportionality, or basically it becomes your growth rate. So that's what you're looking at. So when you see something like this, we can solve a differential equation without actually having to go through the process of doing the integral. All right, this is our last example. Donald deposits $1,000 into a savings account that earns an interest rate of 4.5% compounded continuously. Find the particular solution of the differential equation that describes the growth in the value of this account. So we are given, in this case, the initial amount, which is the P sub 0. P sub 0 is $1,000. Okay, we are given the fact that the K value is 4.5%, but we want to change that so that it's an actual, I know it looks like a decimal here, but we have to make the percentage not in a percent, so it needs to be 0.045. So that's your actual K value. So now all we have to do is pretty much plug this stuff in. It says find the particular solution to the differential equation that describes. Okay, so we've got pretty much everything we need. So we know that P of t is going to be 1,000 e to the 0.045 t. And that's it. There is this method which is called separable differential equations, which I don't believe that we're actually going into in this class. However, if it does come up in your homework, please refer to the book on separable differential equations. And if I need to, I will create another video, a supplemental video showing how to do those.